my talk will look at the strategies we use at English Heritage for the storage and display of copper alloy and iron objects. I will also look at how we go about designing and maintaining good showcases for displaying these material types. The research that I will present is made up of, firstly, data from experiments published in the wider conservation community, and secondly, experiments undertaken by Dave Thickett, who is Senior Conservation Scientist at EH, which incorporates work by our PhD student placement programs. English Heritage holds in trust over 1 million objects that are associated with the 403 sites and monuments for which it's responsible. The policy is to try to display collections on the sites that they are associated with, and to make our stores accessible for public tours and researchers. Many of the buildings have far from ideal environments. By far the largest proportion of our objects are finds from archaeological contexts. This graph illustrates in red that 49% of our collections are archaeology. Looking at published data on safe relative humidity values for archaeological iron, we see a huge range. Some of them appear at the top of this slide. Our conservation scientists recommend that our archaeological iron is displayed at less than 30% relative humidity, and archaeological copper alloy at less than 35%. These parameters are what we aim at when iron objects or copper alloy objects are being displayed without other objects made of other materials, and where different RH parameters are recommended. We aim to achieve lower values in storage using silica gel. Stewart and lock boxes are used. Irregular or larger objects are placed within heat-sealed polythene bags and sealed with silica gel. We're gradually changing our 4-spot indicator cards, that's the 10, 20, 30 and 40 type, to the 3-spot indicators reading 5, 10 and 15 for monitoring. Literature states that iron objects will be stable and not corrode below 19% if those objects have been kept below 70% RH since excavation. That's research from Dave Thickett, 2013. Only the presence of acacanite formed above 70% will lower that threshold. So a note to dry your iron finds as soon as excavated. Dry objects before placing them in the microclimate. Our science team carries out analysis so that we have a strategy of how we manage these material types. This graph is from tests with powder compounds to mimic archaeological iron material. Results were also confirmed with a large survey on objects. Below 16%, there's no reaction. Below 30%, it's very, very slow. And a dramatic increase is shown at 30 to 35%. This rapid corrosion between 30 and 35% is very important for our EH strategy. This is why we aim to display iron at less than 30% RH. Another increase above 45% is temperature dependent. Oxygen consumption measurements have been applied to both iron and copper alloy artifacts to measure and predict their reactivity at varying relative humidities. When iron or copper alloys corrode, the fuel in that process is oxygen. So if we can measure the oxygen that is being used up, it gives us a good idea of how quickly the object is corroding. These analyses have allowed us to safely display non-reactive material without low humidity control and to guide the strategy needed for the most vulnerable material. This graph shows the changing corrosion rate with relative humidity amongst iron objects. Each point is a different batch of 8 to 12 objects, excavated from 2 sites. They're on the green and blue lines. Credit to David Watkinson at Cardiff University for this research. It shows oxygen consumption rate on the vertical axes and increasing RH on the horizontal. As you can see, the iron objects from one site, green, started to corrode in a small way at about 30%, and then in earnest at about 50% RH. The objects from the other site started to, sorry, I have to go on back. Go back. Oh yeah. Sorry about that. The objects from the other site started corroding at about 60%, but really got into their stride at 70%. So the rate of salt-driven corrosion of iron is strongly correlated to the RH. However, the values can vary with material from different contexts. On this graph, we can see the equivalent for copper alloy. This is Thickett's research, which also fits in with about 3 other people's research. RH, again, is the key factor in which cuprous chloride reacts to cause active corrosion. Different studies have produced different thresholds for the start of the reaction. Data from English Heritage and British Museum research shows that there is a risk above 35% relative humidity. As this graph shows, on vertical axes we have oxygen consumed, on horizontal we have increasing RH. And as you can see, it's at 35% RH that we start seeing the big uptick in oxygen consumption and therefore corrosion. High levels of acetic acid. These can be found in timber composites, paints, adhesives, are known to cause corrosion above 54% relative humidity. The vertical axis shows oxygen consumption. The horizontal shows concentration of acetic acid. So the green triangles are 33% RH. You can see they stay along the bottom axis. There's no reaction. So at 33% RH, there is no corrosion with acetic acid. The red dots show 54% RH, and the blue dots show 75%. So with these, you can see reactions happening, equal corrosion. This is how we test oxygen consumption. So the photo on the right is of a conical flask with an iron object being tested inside with art-sorbed silica gel to maintain a 50% relative humidity level during the test. The middle lower photo shows the same process with an array of larger objects encapsulated in heat-sealed Escal bags with art-sorbed cassettes to control the RH. The photo on the left shows testing of the oxygen level. The graph is from Dave's research. For the English Heritage Iron Collection, we found 40% tested was unstable and follows the response shown previously. Approximately 60% doesn't respond at high relative humidities. Oxygen testing is picking out those objects that are stable and we don't need to do anything for. We take an oxygen reading at the start of the measurement and then another one 2 weeks later. If corrosion is happening, oxygen is used up, and so the oxygen level will be lower. This would tell us the object is not suitable for display in ambient RHs. If the iron and copper alloy objects tested show no oxygen consumption after 2 weeks, then we raise the RH to 75% for 3 days and test again. This allows us to display stable metalwork with organic materials at around 50% RH. And this is the kit we used to read the oxygen levels. The pink spots go inside the container, and we read the oxygen level through the glass or Escal with fibre optics. The image on the left shows an object within a heat-sealed Escal bag, art-sorbed silica gel, and with an orange oxygen spot. And now I'm going to talk about showcases. A standard of showcase has been developed to enable low relative humidity atmospheres, that's less than 30% relative humidity. To do this, we carry out air exchange rate tests. We use predominantly passive control methods, i.e. silica gel. We specify inert materials, and we install standalone and telemetric environmental monitoring within each case. The EH Conservation Science team have worked to develop low-cost measurement methods for air exchange rates and leak detection. Conservation scientists work to model the relative humidity inside showcases in relation to the external environment, and this has guaranteed the safe display of a wide range of artifacts in rooms that can have aggressive environments. The design of showcases is critical in achieving good environmental control. Principles are airtightness, that's air exchange rate. Factors such as size, hinge location, lock positioning, and seal types are all part of this consideration. Space for desiccants. RH materials should be placed in a compartment separate from the main display space. The compartment must be big enough to hold enough conditioning material for the display volume. This can be calculated from web pages. Air circulation. Movement of conditioned air from the lower compartment to the display area is vital. Baseboards separating the silica gel compartment from the display area should be perforated, with holes covering at least 25% of the area. Pollutant materials. Avoid materials that are known to emit pollutants, i.e. wood products that emit organic acids. And case dressing. Paints, fabrics, adhesives, and graphics for use in showcases must be tested, body tested. And when applied, enough time should be left for solvents to dry and off-gas before objects are installed. So that time needs to be written into installation programs. These images show carbon dioxide loggers being used in a display case at Aldeburgh to assess the air exchange rate. So air exchange rate is a measurement of how airtight a case or a storage box is. It describes how long it takes to replace the air in the case with air from outside and is measured in air changes per day. So a low air exchange rate is good air tightness. Desiccant material will last longer, but will increase risk of any pollutant buildup from sources inside the case. High air exchange rate equals poor air tightness, can make RH control very difficult to maintain long term and increases the influx of external pollutants and dust. So air exchange rate can be measured in several ways, but one of the simplest ways is using a tracer gas, such as carbon dioxide, injected into the case. The carbon dioxide concentration is monitored using a logger inside the case to measure the time it takes to disperse. This is stuff from European standards. The air exchange rate column is second from the left. At English Heritage, we generally specify cases to have 0.4 air exchange rates. This significantly reduces monthly and most seasonal variations with a medium amount of passive control. So for some passive control air movement case studies, this graph shows a case at Dover Castle with a solid baseboard with a small gap around its edge. It doesn't work. There isn't enough air movement from the silica gel unit into the main display area. So the top line shows room RH, which is in the 70s. Below that you have the display case RH in the 50s. Then red and pink line is temperature. And then the light blue line at the bottom is the silica gel unit RH, which is less than 5% RH. So we have 5% in the silica gel compartment and 50% in the display volume. It's not great. With introducing 8mm holes throughout the baseboard of the case, you get the RH of the display volume more or less corresponding to the RH in the silica gel drawer, which is what we want. It's the bottom two lines of this graph. And this side shows the same case as previously, but with smaller 5mm holes in the baseboard, and illustrates that the size of the baseboard holes make a difference with exchange, and that 5mm holes don't work. The case volume reading about 30% RH, compared with the silica gel unit of around 5%. So to summarise, low height cases equal lower air exchange rate. And a desktop case is best for archaeological iron and copper alloy, and a lower back hinged case top is best. If you use larger cases, pull and slide doors are better than hinged long term. And for passive RH control, you need low air exchange rates, so 0.4 a day. Lots of space for silica gel, access to change the silica gel without interrupting the case display volume, and good air exchange between silica gel and display volume. 8mm holes covering 25% of the base board. We use 3mm metal baseboards, perforated ones. If you do have solid baseboards, then we found that 20mm slots around all the sides work. If you've only got 2 slots available to you, then 30mm slots work, and 13mm for MDF boards. And you need the silica gel near the display volume. Thank you.